The very last part of section 9.1 talks about monotonic and bounded sequences, and this is something that you're going to see throughout your study in higher mathematics, so it's a disappointment that it was left off of the previous video. It's not a crazy or difficult concept. The first concept is monotonic, and monotonic sequence just means that it's continually increasing or non-decreasing, and it's or continually decreasing or non-increasing. So essentially what we're saying is a sub 1 has to be less than or equal to a sub 2, less than or equal to a sub 3, all the way through a sub n. Or obviously it could go in the opposite direction. The key here is that you're never going to have a value that's bigger than the next and then less than the next, because that would not be monotonic. Oops. So we get the idea that it's either continually increasing or continually decreasing. So that's what we're going to do first, is just take a look. Now, you can obviously reason through these. You can say, well, what's going to happen here? Negative 1 to the n, we've talked about this already. We know that this is going to be a negative 1, and then it's going to be a positive 1, and a negative 1, and then a positive 1. And so it's clear before I do any kind of work at all that if I take 4 minus negative 1, 4 minus positive 1, that's not going to be strictly increasing or strictly decreasing. But remember that you can always just do the work and actually figure out the first few terms to find the pattern. So 4 minus negative 1 to the first, we already said that's going to be 4 minus negative 1, which is going to be 5. And then a sub 2, 4 minus negative 1 squared, which is 4 minus 1, which is 3. And then a sub 3, 4 minus negative 1 to the third. Negative 1 to the third is negative 1, which gives me 5. And we can see that this is going to be an oscillating function. It's going to go back and forth between 5 and 3 and 5 and 3 and 5 and 3, and it's just going to keep happening. So this is not monotonic, because it's not strictly increasing or strictly decreasing. It decreased, then it increased, and then it's going to decrease, and then it's going to increase. And again, we call that an oscillating function, if it oscillates back and forth between different values. Now let's take a look at example B. And again, feel free to either find the values and see the pattern, or you can reason through it. So let's just find the values first. This would be 5 times 1 over 1 plus 3, which would be 5 over 4. So just a little bit over 1. A sub 2, 5 times 2, 2 plus 3. That's 10 over 5, which is 2. So obviously that increased. Now let's see what's going to happen with a sub 3. 5 times 3 over 3 plus 3, which is 15 over 6. 15 over 6 is the same as 5 halves, and obviously that increased again from 2 to 2.5. And I can keep finding as many values as I need in order for me to be convinced. But as I can see, this value is growing at a higher rate than this value. So this number is going to keep getting bigger, and so is this number, but this is going to get bigger faster. And so it's very clear that this is going to continue to increase. So this is monotonic. Keep in mind that we also know how to find the derivative of a function. So using example B from our last slide, looking at the sequence of 5n over n plus 3. Remember, I can look at that as a function, f of x equals 5x over x plus 3, and I can find the derivative of that function. And you can see I've just used the quotient rule there, and I have found the derivative. Now, why is the derivative helpful? Because we know that the first derivative of a function tells us if that function is increasing or decreasing. So if the function is positive, then it's increasing, and if the function is negative, then it's decreasing. By finding the derivative of this function, I can see that no matter what I plug in for x, it's going to be squared. So I've got 15 over some positive value, and 15 over a positive value is always going to be positive. So because this is always positive, this is always increasing, and therefore it's monotonic. The other characteristic we need to talk about is whether or not a sequence is bounded, and it can be bounded above, bounded below, or bounded both above and below, which we would just call it then bounded. So looking at our first example from our previous slides, remember that this oscillated between 5 and 3. And so this is obviously bounded both above and below, because we could say 3 is less than or equal to a sub n is less than or equal to 5. In our second example, this is also bounded, so this is called bounded because it was bounded both above and below. In our second example, remember we found 5/4 and then we continued, and we didn't ever find an upper bound, but if we continued, and it would take us a while to get there, if we continued, we would find that 5/4 is obviously the very lowest that we could get because we decided this was monotonic. So it's continually increasing. Oops, I think I spelled that wrong. Monotonic. And if we continued and continued and continued, we would find that this gets continually closer to 5. So this is also bounded. It is bounded above and below. So the very last theorem that I wanted to talk to you about in section 9.1 then is theorem 9.5 that essentially says if you have a sequence that is both bounded and monotonic, then it converges. So let's look at that before we actually look at our example. If we know we have a function that is monotonic or a sequence that is monotonic, remember monotonic tells us that it is going to continually increase, 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 or decrease, decrease, decrease without end. Now, if it's also bounded, that doesn't mean it's going to stop increasing. That just means that it's going to be increasing at smaller intervals. It's going to continue to get closer and closer and closer to some value, and that's the value that bounds it. And therefore, we know that that's going to be the limit, that it converges to that limit. So this example, which was our second example that we did, back at the beginning of this video, is a great example because we talked about the fact that it was monotonic, it was continually increasing, and I can see again by the graph that it is increasing. And we did talk about the fact it was bounded. It's bounded by 5, and so you can see I drew in this line y equals 5, so you could just see visually what was going to happen. But because this sequence is both bounded and monotonic, and then it converges, and it always is going to converge to the bound. So in this case, because it's monotonically increasing, then it's going to have an upper bound, and that upper bound is 5. That's what it converges to, which means that the limit of this function, the limit as x approaches infinity, of 5x over x plus 3 is 5 because it converges to 5.